This is Saiki Louie. I'm calling in from Boston. I'm sorry I can't be here, but I'd like to thank Marcus and Martin and the organizers of CogSci to make this wonderful symposium possible. So we know that the world knows and loves music, right? Music is really one of the central facets of human culture. People who who don't have any explicit experience in musical training might still love to go rock out at concerts. And music is quite literally all around us. And even from day one, the infant brain shows signs of having some musical knowledge. And music is also celebrated, not just produced, but celebrated all around the world. And even in some non-human animals, it seems like they might have some understanding of human music, suggesting that this might be a phenomenon that's not just unique to humans. But there are some exceptions. I'm about to play you Happy Birthday song sung by a tone-deaf individual.
Happy birthday to you, happy birthday to you, happy birthday dear Psyche, happy birthday to you.
So tone deafness is also known as congenital amusia, and it's characterized by the inability to sing in tune. Now, 17% of college undergrads think that they have tone deafness and that they're pretty bad at singing. However, the standardized psychometric test called the Montreal Battery of Evaluation of Amusia, where you get two melodies and you just have to say whether the second one is same or different from the first. 4% of the normal population fails that, so we really think that the incidence is somewhere in between 4% and 17%. And then we also have this pitch discrimination test that we've implemented on musicianbrain.com/pitch test, where you get pairs of pitches and you just have to say it, whether the second one is higher or lower than the first. And then the algorithm converges towards your threshold of pitch discrimination. And if that threshold is larger than one semitone, which is quite rare, we identify these individuals as being tone deaf. These cases of tone deafness really beg the question of what do these people know and not know? What is the source of musical knowledge that they might not have? And I think most people will agree that pitch is a major source of musical information. Musical systems all around the world have pitches. And intact pitch perception, the ability to sense these pitches and infer from it a musical experience is quite important. It's very fundamental to musical knowledge. But pitches don't exist by themselves, right? They also exist with certain frequencies and probabilities. And if these pitches co-occur at the same time, then that gives rise to harmony. And if pitches occur one after another in sequence, then that generally gives rise to melody. Now, so it's really these frequencies and probabilities of occurrences of pitch that we need to be understanding. So how do we go about trying to understand how the brain learns the frequencies and probabilities of pitches? Well, as we said in the beginning, most people have already had so much exposure to Western music that even people without musical training show lots of implicit knowledge of the frequencies and probabilities of Western musical sounds. So what we really need is a system that allows us to test learning with a new set of frequencies and probabilities that are not within Western music or really within any musical system in the world. And this would give us a high degree of experimental control so that we can really systematically manipulate what these frequencies and probabilities are that they can get exposed to. Now, to that end, in the past few years, we've developed this new Martian musical system. It's based on a different musical scale. It's called the Bohlen-Pierce scale. And then we think that by comparing tone-deaf individuals and matched controls in the way they learn the statistics of music, we can really get at the degree to which the different types of musical knowledge might be learnable. So the Bohlen-Pierce scale is the basis of our new musical system. Just to review, the Western musical system is based on a 2-to-1 frequency ratio known as the octave. So an A that is twice the frequency of an A that is 220 hertz is 440 hertz. And within that 2-to-1 frequency ratio, we have divided that ratio into 12 logarithmically even steps. So it sounds like this. contrast, the Bolen-Pierce scale is based on a 3-to-1 frequency ratio. So one tritive instead of one octave above the 220 hertz is 660 hertz. And within that frequency ratio, it's 13 logarithmically even divisions. So the scale sounds like this. Now, what this Bolen-Pierce scale allows us is to find out is to derive some new chords that actually have completely different mathematical ratios from existing music, but it still sounds good, right? It still sounds psychoacoustically plausible because it's based on low integer frequencies, frequencies that are related in low integer ratios from each other. And so by applying the rules, so here we have a set of 12 nodes. Each node goes into n in this previous formula to derive one frequency. And within these 12 nodes, what we could do is we could iterate through them, or we could have them move forward to the next set of nodes. They cannot go backwards, right? So there are thousands of possible melodies that you could generate from this one system. One possible melody is right here, so you could go 6, right, and then you could go to 4, and then you could move up to 7, and 7, 7, and then you could go to 6, and then you could move up to 10, and then you could repeat itself. So this is what one possible melody sounds like. And I should emphasize that in this system, we're really controlling for frequencies of tones without and manipulating the probabilities of tones. You can imagine, given this one chord progression, 0, 6, 10, 0, 4, 7, 3, 7, 10, and so on, you could have another chord progression that is just the reverse, right? So starting from 0, 6, 10, then moving forwards to 3, 7, 10, and then 0, 4, 7. So you could have an anterograde grammar, and then you can have a retrograde grammar. So using these two grammars, you could really create a parallel set of two musical worlds. So given this system to generate thousands of melodies, we can now ask the question of how we can learn, whether we can learn the Bolen-Pierce scale. So the general design of our behavioral studies is quite simple. So people come into the lab, we do a pre-test to assess the baseline knowledge that they might have, and then we give them exposure to melodies in one of two grammars. So either, we also have a no exposure control condition, but we could have either exposure to the grammar 1 or grammar 2, and they get 30 minutes of exposure. And then after exposure, they can get a post-test where they assess, we assess learning. And then, of course, by comparing the post-test and the pre-test, we can get an understanding of what they know, since they've been exposed to melodies in the grammar. Now, the first set of questions we asked were really getting at the question of how sensitive are people to probabilities. So the first question is, can you remember old melodies? So if I gave you one melody and then I gave it to you again, can you say, oh, that sounds familiar? So that was assessed using a 2 alternative forced choice test of recognition. People were given pairs of melodies, one of which they had heard before and was grammatical, and the other was not grammatical and that they had not heard before. So and the question posed to the participants was always say which one sounds more familiar. So if you recognize the melodies that you'd heard, you would rate the one that you'd heard as being more familiar, quite obvious. We could also ask, can you learn new melodies, right? So given two melodies, neither of which you've heard before, but one is grammatical and the other is not, can you actually pick out the one that is grammatical as being more familiar? And in a sense, this is a more deep test of probability sensitivity. So neither melody that you're given has been heard before, but one is legal given the grammars that generated the melodies we just heard, the other one being not legal. So endorsing the melody that the grammatical melody as being more familiar would suggest that you have gained something, you have learned something about the underlying grammar. So here are results from a set of experiments, really, in general, showing that if we have a few melodies that were repeated many, many times each, so such as on the left of this graph here, 5 melodies repeated 100 times each, people were at ceiling, at recognition. So they really recognize those 5 melodies they'd heard, but they're quite pretty much at chance in generalization. So they're not able to generalize their knowledge towards new instances of the same grammar. Now this pattern sort of falls off or trades off, and there's a double dissociation between learning as measured by recognition and memory. Learning as measured by generalization and memory as measured by recognition. So the more melodies you get, the less you recognize each of them. And the fewer repetitions you get, the less you recognize each of them. But the more melodies you're exposed to, the more you tend to generalize. So when you get 400 melodies, which you heard one time each, then the chances that you're able to learn the underlying structure are actually quite high, and then learning and memory actually become statistically indistinguishable at this rate. So we've done several follow-up experiments, one of which is looking at disrupting harmony and how that might change the learning abilities. So recall that I've mentioned earlier that the Bohl-Impaired scale is based on a 3-to-1 frequency ratio, and with a starting point of 220 hertz. And then within that 3-to-1 frequency ratio, we've divided that ratio into 13 logarithmically even steps. Now, what this forced octave scale tries to do is take a 2-to-1 frequency ratio, so an octave, and then arbitrarily divide them into 13 logarithmically even steps, just like in the Bohl-Impaired scale. So this really disrupts the perfect ratios that the Bohl-Impaired scale is set up to accomplish. And now in this forced octave scale, you could still have the same notes, right? But you're actually not... the chords are not actually harmonically related to each other, which results in harmonic musical system. But it turns out, surprisingly, that people were still able to generalize their knowledge. So it seems like the harmony was not actually helping people learn the new musical system. Or in other words, people were using information that's not strictly related to harmony. Another follow-up we did was to disrupt melody by eliminating some select transitional probabilities. So recall that I've mentioned that the artificial grammar system is based on these either interrograde or retrograde chord progressions that were related to each other, and that could either repeat themselves or move forward to the next next notes in the musical system. Now, we actually arbitrarily eliminated some of these pathways in the artificial grammar, and when you do that, it turns out that people stop being able to generalize. So people were at chance in their learning of the new musical system if some of the pathways in the musical system were eliminated. So this is really suggesting that it's transitional probabilities that the learning mechanism is picking up on. So I've talked a lot about probabilities, transitional probabilities especially, but now we could also discuss a little bit about frequency sensitivity. Right? So what is it that people are learning? Is it are people learning to expect some frequent tones within the musical system? So this could be assessed using a probe tone ratings test, which has been around since Krumhansel's work from the 80s and 90s. And so you could, in general, people are given a melody followed by a tone. The trial sort of sounds like this. Right, and your task is always to rate how well that last tone fits with the preceding melody. Now, Krumhansel had shown that if you give people a C major melody or C major scale, then people rate C as being best fit, G as being next best fit, and so on. If you give people an A minor profile, then people rate A as being best fit, and so on. And these probe tone profiles that you could generate from people's ratings actually reflect the statistics of songs in the repertoire, right? So major and minor profiles actually fit quite well what people's expectations are. Suggesting that people really have built up some long-term statistical sensitivity based on their exposure to music in their world. Now, you could do that, these types of proton ratings, with the Bowling-Pierce scale too, and that now we really know that this is a short-term type of learning, that people are acquiring this new musical system on the fly as they're being exposed to it in the lab. Now, again, so the way I'm plotting this is that each of these on the numbers on the x-axis plugs into n to form one frequency, one tone rather. And in red, I'm showing the exposure profile. So they heard note 0, around 1,000 times, and so on. Now here's what people rated before they heard the exposure corpus. This is the pre-exposure ratings. You can see that there's some correlation between ratings and the exposure, but not much. Now this is what people rated after they had exposure to the new musical system. Now this purple line is now a lot more closely correlated with the red line. And now if you only plot the correlation between people's ratings and the exposure profile, you'll see that there's a significant increase in exposure in correlation after exposure, suggesting that within a half hour of exposure to new music, people were able to learn something about the frequency structure of the musical system. Now, the next follow-up was to apply this statistical learning rating system to tone-deaf individuals, right? So we had 15 tone-deaf individuals and 20 control individuals that were matched for age and sex and number of years of musical training. This is work by Jan Iyer in her senior honors thesis. And we had a similar type of design where people came in for a pre-test and then a 30-minute exposure and then a post-test. And this was done on tone-deaf individuals and controls. And we did this on the probe tone test where people were given a melody and then a tone. They just had to rate how well the tone fits the preceding melody. So just to review, this is results now in the new data set from control subjects. Again, black is the exposure profile, so this is sort of the ground truth that their ratings are supposed to simulate if they've learned the musical system quite well. And pre-exposure ratings are not quite so correlated with the exposure profile, but post-exposure ratings are quite highly correlated, right? So the purple line is quite highly correlated with the black line. Now in tone-deaf individuals, here's the pre-exposure ratings, here's the post-exposure ratings. So there really doesn't seem to be quite as much of an increase in correlation after exposure. Now this is just the correlation between the ratings and exposure. And you could see that both groups actually had some increase in post-exposure ratings. However, there's also a difference in post-exposure ratings between controls and tone-deaf individuals, suggesting that tone-deaf individuals were not able to learn quite as well as the control individuals. And interaction between the group and the pre-post ratings was significant as well. So really, it seems like the tone-deaf individuals were learning a little bit, but not quite as well as the controls. Now, I've mentioned that the Montreal Battery for Evaluation of Amusia, or the MBEA, is a measure of tone deafness, right? So if you get these pairs of melodies and you really can't tell the difference between them, then that suggests that you be tone deaf. Now, so just to reiterate, this is one example trial of how the Montreal Battery sounds. So who thinks those two melodies were the same? Who thinks those two melodies were different? Well, I can't see you guys, but I hope that most of you thought that the two melodies were different. And it turns out that people's performance on the Montreal Battery, specifically on the scale subtest of the Montreal Battery, was positively correlated with people's post-exposure probe tone correlation. In other words, the better you are at telling these two melodies as being same or different, the better you tend to be at learning, at showing statistical sensitivity to the frequency structure of the new musical system. So the next question I wanted to ask was, what are the neurosubstrates of music learning, right? So a lot of people have looked into brain differences between people who are tone deaf and people who are matched controls, and the general take-home message has been that there's a differences between the superior temporal gyrus, or the STG, in the auditory areas, and the inferior frontal gyrus, or the IFG, which is more important for cognitive processing of sounds. Now, our hypothesis is that there might be a connection between these two areas that might be driving these differences at the endpoints of such a connection. So really, brain connectivity is what we wanted to be looking at. And the best way to do that is using diffusion tensor imaging, which is a type of magnetic resonance imaging that capitalizes on the diffusion properties of water and the directions in which water tends to diffuse in order to gain information about about the connectivity between and within brain areas. And so using the information about where water tends to diffuse within each volume pixel of the brain, you could reconstruct all the major pathways of the human brain. And the pathway that we're most interested in is called the arcuate fasciculus, which since the 19th century has been known to connect the Broca's area and the Wernicke's area. So, and if you have a stroke and you don't have an arcuate fasciculus, then you tend to be unable to repeat words that are spoken to you, right? So it seems like people have thought that the arcuate fasciculus is an important pathway for language. So we got some tone deaf individuals to come in, and we got this DTI scans on them, and then we recorded. We drew regions of interest over the superior temporal gyrus and the inferior frontal gyrus, and then we identified all the tracts that connected these two regions. And so the tracts that were identified as connecting the STG and the IFG, we labeled as the superior branch of the arcuate fasciculus. And then we also additionally drew the middle temporal gyrus, and the tracts that are identified as connecting between the IFG and the MTG, we identified as being the inferior branch of the arcuate fasciculus. So here is looking at one non-tone deaf control individual in the 3D view. So the nose is around here, the left brain is here, the right brain is here. This is the three-dimensional view. And I've colored the superior branch of the left arcuate fasciculus in yellow. That's kind of hidden behind the pink. The inferior branch of the left arcuate fasciculus I've colored in pink. And then in the right hemisphere, the superior branch of the right arcuate fasciculus, which connects the right STG and the right IFG, I am highlighting that in red. And then in green, I'm highlighting the connections, the inferior branch of the right arcuate fasciculus, right? The connections between the right MTG and the right IFG. Now, in contrast, the tone deaf individual, firstly, you'll see that there's a lot less connections overall. And furthermore, this right superior branch of the arcuate fasciculus that was identified in 10 out of 10 of the control individuals was not identified in any of the 10 tone deaf individuals we looked at. So this is really suggesting that there's a major association between the tract volume or structural connectivity in the right superior branch of the arcuate fasciculus and tone deafness in general. So we further wanted to look at how these tract volumes in the arcuate fasciculus might reflect individual difference in statistical learning. So we got some tone deaf and non-tone deaf individuals all to come back and to do some behavioral tests looking at the generalization and recognition that I talked about earlier in this talk. And we also traced their arcuate fasciculus, and it turns out that the inferior branch of the right arcuate fasciculus, so the branch, the white matter pathways that are connecting the right inferior frontal gyrus and the right middle frontal gyrus, temporal gyrus, was positively correlated with generalization scores. So the people who were better learners tended to have more volume in this branch. This was not observed in when you look at recognition scores. So it really seems like the volume of the right ventral branch or inferior branch of the arcuate fasciculus is correlated with generalization score, but not with recognition. Now, we want to go further than that and say, okay, where along the arcuate fasciculus is it most predictive of learning behavior? So we searched within the volume that is within the brain that is traversed by the arcuate fasciculus across all the subjects of the study. And then we looked for voxels that had fraction anisotropy, which is a measure of white matter integrity, that really correlated with generalization performance. And it turns out that this cluster in the junction, the temporal parietal junction, really showed FA, or white matter integrity, that was predictive of individual differences in pitch-related learning. So in other words, the more integrity you find in this turning point, or this junction of the arcuate fasciculus as it turns into the temporal lobe, the better you tend to be at learning this pitch-related grammar system. So this really means that there might be some implications of individual differences in structural connectivity, and those behavioral implications might apply specifically to statistical learning. So comparing just tracks that were identified from the right superior temporal gyrus, it seems like most of the normal non-tone deaf individuals have track volume that goes from the STG towards the frontal lobe. However, in contrast, the tone-deaf individuals don't have as much connectivity. They might have some connectivity from the right STG to other parts of the brain, and that's what we're still trying to find out. What other regions might be kicking in an arcuate fasciculus that is impoverished in the tone-deaf individuals. Is the arcuate fasciculus sort of miswired and to point towards a different direction, and what behavioral implications might that have? But the take-home is that there are really some structural, individual differences in structural wiring of the brain that might have behavioral implications. Specifically, some people might be better at learning music just because they have a larger and stronger and a more high integrity in their right arcuate fasciculus, and whereas others might not have as high connectivity in the arcuate fasciculus, and that might have some behavioral implications, either for being not as good at learning music, or perhaps even better in some other compensatory ways that we're still trying to find out. So in summary, I think I've shown that pitch is organized in frequencies and probabilities, and these are statistics that we could really manipulate in the lab to try to understand how people make sense of musical systems in their world. And pitch perception is disrupted in tone-deaf individuals, but we also think that the frequency learning of pitch is disrupted in tone-deaf individuals, but maybe not necessarily the transitional probability learning. And we think that this statistical learning system in music is really observed by structural connectivity between frontal lobe regions and superior temporal lobe regions, and specifically in the turning point of such a major pathway in the brain. And so maybe there's something about combining the study of tone-deaf individuals and the study of a new musical system that might be helpful together in giving us more knowledge about how music learning works in the brain. So I just want to point out that the experiments that I've shown, talked about, the Bolen-Pierce scale artificial grammar learning experiments, are now available for download on Figshare. You could also get them from my website, psychelouis.com/publications downloads. They're available in MaxMSP format, and also we have about 1,000 melodies that are included in this battery of tests. So I'd like to thank the people that have contributed to this, especially Jan Iyer and Charles Lee are actively working on the artificial grammar learning studies, both in neuroimaging and in the behavioral testing and neuropsych testing. And I'd also like to thank the funding sources. Thank you very much.